Yeah.
Thanks. Not sure overview.
Not an overview?
I'll try. Thanks to my talk. And it's a little bit of a challenge to talk after Avi. And I guess I should also start off with a little bit of an explanation of how my talk might be connected with the theme of the workshop. But actually, I probably have a slightly easier time because if you look at the exact description of the workshop, there's the word holographic algorithms stated in there. But also partly because of that, perhaps, I feel maybe I should, especially Les is not here, give some introduction, some very elementary idea what the holographic algorithms are and what the flavor of this thing is. And then I would like to move on to some survey, as Peter described, some dichotomy theorems, which are basically classification theorems of very broad classes of counting problems. And these are sum of product type computations or partition functions. And every now and then I would like to point out some possible connections with many of the themes and expertise of the audience who do tensor rank, and there are connections there in many ways, but because of time limitation, I think I'll not really dwell too much onto the exact details of this. So, in some sense, I think the talk would be two parts. The first part will be a very elementary description, and hopefully you get a flavor of what holographic algorithms are. Okay. When Les gave this talk in the very beginning about introducing holographic algorithms, and there was sort of a feeling that, oh my God, he's got some very strange algorithms that will collapse P and P or sharp P and P. And I don't think, in fact, my talk will give you that impression. Rather, I think it gives you an understanding of this extent to which these techniques can do. And by the dichotomy theorem, which will be the second part of the talk, it will try to describe to you that in some sense, the import of these holographic algorithms is trying to carve out exactly what you can do with these techniques within sharp P. So you have a complete classification within sharp P. So let me start with this sharp P. Everybody probably knows, but let me just spend one slide on it. It's basically a counting version of NP. You have a NP is decision problems. Is there a solution? Sharp P is how many solutions are there? Okay. So basically, but I like to somewhat bring your attention to the idea of a perfect matching. Oh boy, this thing went out. That work. So, perfect matching. Okay, I can take this out. That is mine.
You also stand in front of my words you want to highlight.
No, I have to move the slides. That's great, thanks. Okay, so what is perfect matching? I hope to have just a single slide to explain if you're not familiar with. It's basically you have a graph and you're taking a subset of edges so that every vertex has exactly one edge incident to it. Okay, it doesn't have to be on a bipartite graph, even though you're probably most familiar with perfect matching bipartite graph. And there are two amazing algorithms that I would mention that for perfect matchings on a general graph, not just for bipartite graphs, you can actually find if there's a perfect matching. And you can also count the number of perfect matchings on a planar graph. These are two really fantastic algorithms. And then based on the idea mostly about the counting on perfect matchings or weighted perfect matchings on planar graphs, Valley introduced these things called match gates-based holographic algorithms. And they have a certain flavor analogous to like quantum computing. You have fragments of computation that are superimposed one on another. I'll explain some examples later. And they seem to introduce, they seem to achieve some exponential speedups for problems that otherwise you didn't know how to do in polynomial time. And then I would like to move on to basically give you some very simple problems, and you can see the flavor type of problems that it solves. So here's a problem, okay? Here's a picture first, okay? So you have a graph, degree at most 3, and then your task is to consider orientations. Orientation of a graph is to assign a direction of an edge, either this way or that way, okay? Subject to the constraint that at every vertex, it's not the case that everybody coming in, nor is the case that everybody comes out. So 1 coming in, 2 going out, 2 coming in, 1 coming out is okay. It's no sink, no sauce. A very natural question, right? And this problem can be solved to count the number of such valid orientations can be solved in polynomial time. So this comes from a sort of a tradition of these ice problems or something. And this can be solved in this exact case of degree at most 3.
You do have a vertex that has all the incident edges pointing to it. Your dependent vertex.
That would not be a valid. So this is just an orientation, okay. And then you demand. In fact, you should not have degree 1 at all because you can't do that, right? So it's degree either 2 or 3. So here's another such problem. You're given a formula, satisfiability formula, and it's a conjunction of clauses, and there are 3 variable clauses. It's a not all equal on these 3 things. So the local constraint is it's not all equal. Okay, and if you have some other things which we'll probably see later are called constraint satisfaction problems. You have various different kind of constraints, like exact 1 or so counting problem of exact 1, the 3 set question is shall be complete. And this thing says that if it's not all equal per clause, then this actually can be solved in polynomial time. So by this technique again.
So what do you mean by planar formula?
So this was a flat family of formulas that was introduced by Lichtenstein in the early 80s. That you draw down the graph representing the graph of the formula. Vertices represent either literals or clauses, and you connect them. If you can connect them as a planar graph. The reason they have to be planar in this setting is because ultimately it's reduced to the perfect matching problem by Castellian's algorithm that I mentioned earlier, counting the number of perfect matches. So here's a not explicitly sort of a counting problem. You have a graph. You want to remove. There's a typo. It's not a planar graph. In general, you have a graph, and you would like to remove a subset of vertices and their incident edges, so that the resulting graph is a bipartite. So you're given a planar, not necessarily bipartite graph.
Sorry, planar or
planar? Yeah, planar, but not necessarily bipartite. But the point is to remove set of vertices as few as possible, so that the thing becomes bipartite. Of course, it's still planar. If you talk about not the node deletion, but edge deletion, then you can imagine that you have this bipartition of sides of vertices still there, and some edges being removed connecting from left to left and right to right. And that would be a max cut, because you remove as few edges is the same as to retain as many edges. Right, so that problem. And now let me go to this strange problem, if you will. We are looking again as a planar graph representing this planar formula. As you asked, you have vertices and clauses. And it is the best way to think about this graph is it's like a 2-3 regular graph. Okay, every variable occurs in 2 clauses, and every clause has 3 literals, variables in this case, monotone. Okay, so now what you want is to find the number of satisfying assignments to this type of formula. But here you want to find the number of satisfying assignments modulo 7. So it's either 0 or 1 or 2 or 3 or 4 or 5 or 6. So why not is a problem, right? Well, why not is that it's actually known that if you don't ask for mod 7, then this problem is number P complete. So it's as hard. This restriction that I just placed, these twice 3 clause, is not a real restriction in the complexity sense. It's as general as you can. And furthermore, in fact, if you only look for mod 2, so if you want to know it's even odd, I think intuitively you would think that that's easier than mod 7. But this turns out to be NP hard under randomized reduction. It's actually technically a parity P hard.
Do you think this result is a different phenomena than the permanent being easy modulo 2 and hard, seemingly hard for every other modular?
Well, here mod 2 is hard.
No, I know,
Yeah. So.
Do you think it's the same phenomena? That one particular modulus is easy and the other are hard?
Yeah, I think the same
problem. Is it the same type of phenomena or different type?
I don't know. The explanation I was about to show you for the mod 7 comes from a theory of developing the theory of match gates and what holographic transformation they can do. But it's not obvious of mod 2.
Permanent
Yes.
has one easy and lots of hard.
Yeah,
Here it
also
says
here,
one
there is
hard.
only one easy.
One easy.
and then
Mod 7.
Mod 7 is very easy.
7 is particular.
Yeah.
Yeah, we'll see that. We'll see
If I
that.
did 17, you wouldn't be able to.
For 3 set, no, but for the other
But it's
5
a
set,
similar
for
phenomenon, right? It's a similar like that, right?
similar in philosophical sense. I'm not sure of
Actually,
how
Jin-Yi,
to
I mean,
do.
just to connect it more to the workshop, I mean, all of these algorithms are reductions to the determinant, and in that sense, it's very similar. Permanent mod 2 reduces to the determinant mod 2, doesn't reduce mod 3. This problem, again, you're going to reduce it by a series of reductions to determinant, and that's.
By the way, we don't know what the status of this problem mod 3 is.
No, but his point is that there are similarities.
I know, the similarity well taken, but there's a lot of, it's not obvious in the sense that for mod 3 we don't
Could
know.
it be that when you come up with your construction of match gates, that you come up with a system of polynomial equations that has a solution, mod 7, but otherwise not? Isn't that some explanation?
Yeah, that's essentially that's what it is.
Okay, so this is the...
But let me show you the next slides. So you can have 4 set, and then mod 5 works, and then you can have actually mod 15 works, and so the mystery is that it's actually a Mersenne number that is controlling the solvability of the equations.
But you know it's finite number of prime numbers, right?
We know that if you use this approach, then exactly when it is a Mersenne number as the modulus, then you can solve it. I don't have a proof that you cannot do otherwise in polynomial time. That would be the NP versus Sharpe question. So this it's not a lower bound in the sense that I proved to you that for mod 7 in this case doesn't work for the 4th set. I just say that that approach will not work. That approach comes down to a set of polynomial equations and is it solvable in various finite fields. And in this case, mod 15 actually works, both in mod 3 and mod 5. Okay. So now, what is this mysterious thing about the match gates? Well, here's a sort of a pictorial example of a match gate. It's just a graph fragment, a planar graph fragment with some designated external nodes in the outer face. And the edges have certain weights, let's say come from the complex field, but it could be from a finite field if you do everything like that. And then the properties of this graph in its perfect matching, and I'll explain this in a minute, is assembled together to form a tensor. And that will be called the signature of the match. So what are these assemblage of values? You look at the perfect matching value of this, which is you sum over all possible perfect matchings, and for each perfect matching, you multiply the weights of the chosen edge.
You evaluate the perfect matching polynomial on this weighted graph.
You first evaluate the perfect matching polynomial on this whole graph. That's one entry of your tensor. Okay?
Are there signs in that perfect matching polynomial? You take signs or no?
No. You just take the sum of the products of the weights. Now, the weights themselves may be negative, but, but you don't introduce plus minus ones. And then you remove some external edges. Let's say you remove this, and of course you remove the incident edges as well. So you end up with this graph, this part. This is just introducing a weight. And then you evaluate your perfect matching polynomial on that again. Okay, that will be another entry of your tensor. Okay? Now, by the property of parity requirements on perfect matching, a graph has a perfect matching if and only, at least it has to be of even number of vertices. So if you had a non-zero value for the perfect matching polynomial evaluation, which is a non-empty sum of the product, then you can't remove just odd number of external vertices and still expect to have a non-zero. So I'm asking you to consider all 2 to the 4 different ways of removing external vertices in this particular case, and there are actually at most 8 entries would be non-zero. Make sense? Okay, so that you assemble together into a tensor of arity 4. So formally, a planar match gates is basically a weighted graph with some external nodes with an embedding of a planar embedding. And you think about these external nodes either as output nodes and input nodes. Now, at this point, it makes no difference. It's just external nodes, and you assign perfect matching evaluation on the graph fragments after you remove certain number of external nodes. The distinction of considering as output or input or generator recognizer in this language is that you are going to later on to transform them as either contravariant tensors or covariant tensors. So you're going to transform positively or by the inverse matrix it's tensor, by the way. Okay? And you'll see that why this makes sense. So technically they come into different varieties, but at this point it doesn't. So now this is the polynomial I referred to. You sum over all possible perfect matchings of the products of its weights over the edges in the perfect matching. And then you think of a subset of the external nodes. You remove that subset of the external nodes from the graph, and you get a subgraph, and then you evaluate that perfect matching same polynomial on that subgraph. And this gives you an entry in your tensor. And these entries are indexed by subsets, and you assemble them together, and that is called the standard signature. Okay, so is that clear? So a match gate is just this planar graph fragments with weights, and you have external nodes, and you think of all possible ways of removing external nodes, and you consider perfect matching properties of those. The reason you're going to consider these removal is that basically you're going to connect these match gates piece by piece together in this big, huge graph where you're going to think about all possible ways the entire graph's perfect matching is going to come out about. And they will be classified into how these nodes are going to be externally connected or internally connected. And when it is externally connected, it's effectively the same as removing this vertex from the consideration of the perfect matching within. Okay? So,
kind of tensor? Is it because evaluating the polynomial just yields a number? No.
So at the moment, I have not talked about, the tensor transformation. Really, it's just this is what's called the standard signature. So it's just directly combinatorially defined by the perfect matchings. Okay. Hopefully, it will be.
G prime is
G prime?
What's G prime?
R sub S.
Oh, R. It should be R. Sorry. Just either a recognizer or a generator. The reason I have these two things is because one is going to be transformed later on by basis transformations contravariantly, and the other is going to be covariantly, and they're going to come together. Okay. Hopefully some example will become clearer. So suppose they have a proof, and hopefully a joke too, and hopefully they're not the same. But in fact, I'm about to give you perhaps the same, and you'll be the judge if it is, okay? So we're going to have an attempt to collapse sharply with P. This, as I told you, I'm trying to give you an intuitive sort of guided tour, and some of this is from dating the back days of when we start looking at them. And these are pretty, strange algorithms, if you will, and you'll see that it sort of just misses, and the question is that a good thing or bad thing? And I would like to argue that it just misses and gives us these dichotomy theorems. Okay. So again, you have an instance, and here's an instance. Think about this as an instance. Okay, you have variables coming into clauses. There's a planar graph. Okay, and what you want to know is the number of satisfying assignments to this. Is it clear? So you have this big graph, and of course, by definition, the size n. That's the definition of the input size. But we're going to allow yourself to do some juggling transformation as long as it doesn't become more than polynomial size. That's polynomial time reduction, right? Okay. So we're about to replace these pieces by match gates. So imagine that these pieces are going to be pieces of this graph fragments that I displayed to you. And now think about all the possible perfect matchings of this graph. And you classify them according to whether or not this edge is in, and this edge is in, and this edge is in, and this, okay? You disregard what happens in the perfect matching within. And then it becomes an exponential sum of all possibilities how the perfect matching intersects with these external connecting edges. And for the given pattern of the external connecting edges, what is the perfect matching of the whole graph that is consistent with that? And now a moment reflection, I don't know if it's a moment, but some thinking will convince you that it's in fact the sum over all these external patterns, there's an exponential sum already there, of the products of the all possible internal exponentially many possibilities of perfect matchings. And every one of the perfect matchings with its weight, assembled together when you multiply, it constitutes a global perfect matching that's consistent with this external pattern. Make sense? So this whole sum then becomes a sum over these external patterns of the signature entry that I just told you what the signature entry is this internal perfect matching assemblage of all possible sums of perfect matchings of their values. And you multiply them all out, that will give you the perfect matching value of the whole thing. And by Castellian's algorithm, you actually can compute that in polynomial time. You don't compute that by actually summing over all possible external patterns and trying to assemble them, right? But theoretically, mathematically, it's the same quantity. And you compute this otherwise by the Castellian algorithm. Okay. So now let's look at what we want in this particular case. You have OR of 3 literals and so on, right? So what is an OR? Well, we computer scientists would say an OR is just a truth table of 0, 1, 1, 1, 1, 1, 1, 1, right? It can't be any simpler than that. You see, it's indexed by 3 bits. 0, 0, 0 gives you no. Okay, I don't like the 0, 0, 0. That's the OR function. At least one of them has to be 1. Make sense? It's very elementary here. So this entry will be 0, 0, 1. This will be the 0, 1, 0, and so on and so forth. Does that make sense? So this is the Boolean OR function on 3 bits. Okay? Now, what about a variable that is going into 2 clauses? Well, the variable can either be 0 or could be 1. But it cannot be 0 and 1. Right? It has to be consistent. So it is represented by this particular vector. It's indexed by 0, 0 or 1, 1. 0, 1, 1, 0 are forbidden. Okay? It's the binary equality function. It's the variable appearing consistently on clauses. Good? So that's how you're going to assign. You're going to assign the signature here and the signature there. This is going to be the Boolean OR signature, and this is going to be the equality signature on the variable. Okay? So So let's look at a schematic instance. This is too simple to be of any real interest, but it illustrates the idea. You have 3 variables on the left and 2 clauses on the right. And what you want is to consider all possible ways of these 6 edges, 2 edges coming out of x, 2 edges coming out of y, 2 edges coming out of z, that are either 0 consistently or 1 consistently per each variable. Right? You have 2 to the 6 possibilities, and you really have 2 times 2 times 2 valid possibilities. Okay? On the other side, you have these 2 conjunction of clauses where both are an OR of 3 bits. Right? So this thing says I want to have at least 1 1 coming in. So it's the 0 1 1 1 1 1 1 1. And I want this thing to be 0 1 1 1 1 1 1 1. Okay? And so what's the Boolean AND on these 2 constraints? You just do the tensor product. Is that clear? So this is how tensor product now comes in. You have an A-dimensional vector, tensor A-dimensional vector. Both are the representation as a truth table of the Boolean OR bits on Boolean OR on 3 bits. And when you multiply, it wants to be both to be true. So the product is a 0 times 1 or 1 times 0 or 1 times 1. You want it to be so it's 1 times 1. You want both to be yes. Yes? Stop me if this is not clear. I mean, this should be, okay? All right. So on the left-hand side, you want a consistent configuration coming out, which is going to be the tensor product of these 4-dimensional tensors or vectors. You have 3 of those. And an entry is going to be 1 times 0 times 0, for example. Okay? What you want is a 1 times 1 times 1. That will correspond to x being false, false, y being true, true, and z being true, true. Okay? So that will be a consistent assignment of all 3 variables. And this whole 64-dimensional vector will have 0 1s, and every entry will be a 0 1 in this particular case. And it will be non-zero if and only if it corresponds to a valid assignment of all 3 variables. And on the right-hand side, you have these 2 Boolean OR you want to do the tensor. So you also get a consistency issue on both being satisfied. Okay. All right, then what you want is to do this dot product. It's a 64-dimensional dot product in this tiny case here. Okay? And then the entry in the product is going to be 0 1 times 0 1, and it will be 1, both 1 if and only if both are consistent. So it's a consistent assignment that satisfies both clauses. And when you sum them all up, then it becomes the number of satisfying assignments. So if you can compute this whole thing in polynomial time, as I told you, it is sort of like looking at as a match gates. So therefore, you can perhaps compute the whole thing as a global perfect matching by Castellian's algorithm. Then you would have been able to compute this whole thing in polynomial time, and then you would have solved the Sharpe hard problem. So this was our joke. Come on, smile. I mean, right? Okay. Now, of course, the kick is that there are possibly match gates for one, but not for the other. I postulated there are match gates that will give you this signature, but it doesn't in one side or the other. One side does, but the other side doesn't. So then there's this next idea, which is you do some basis transformations to perhaps make it so that it's realizable. Okay, so this is the real name of holographic algorithm comes in here. So we are going to do a transformation on the basis, and we're going to think, and this is why it's not just assemblage of values, I'm thinking of it as a tensor, because I'm going to subject to a transformation of either the contravariant or the covariant tensor. Okay? So at this point, I will think about this formally. I have a tensor that's subject to a transformation by matrices. And I'd like to, for example, realize this 0, 1, 1, 1, 1, 1, 1, 1. Okay, I want to be it so that after the transformation, it's actually a 0, 1, 1, 1, 1, 1, 1, 1. There are no match gates that will directly do this, but I want to show you that it's possible to do it after a transformation. Okay? Now, what is good about the transformation? Well, this product, this dot product, is going to count the number of satisfying assignments. That's the quantity we want to compute. And if it is somehow made into a match gates thing and match gates thing, then I can compute this thing without multiplying out this exponential sum. I'll do it differently, right? But for this dot product, I could transform it just by the middle by inserting some invertible transformation matrix T to the tensor 6 in this case. And by tensor product, it distributes. So I can do this T to the 6 by T to the 2, T to the 2, T to the 2, and this T inverse to the 6 to T to the inverse 3 and T to the inverse 3. This is just a mathematical equality. No computation taking place here. Okay? This is just a mere stating of a fact that the two quantities are the same. And the problem without this earlier in this slides was that I can't quite get match gates to do both sides. Actually, I can do this side, but I can't do this side. And now, what if after the transformation, after suitable choice of the T, I could actually produce a match gate whose 8th entry is in fact the signature of an external, 3 external vertice match gate signature. Okay, so that's the point. And if I could realize that, I can find a T, and I somehow produce a match gates for you, and its signature is this. Why it's called holographic, you'll see in a minute. Because I'm sort of combining the truth value of the actual perfect matching values by the entries values of the T, this strange T, whatever it is, okay, the transformation. So let's think about this. So at least now, mathematically, we want this. And we want to find a certain basis transformation, which is a 2x2 matrix, okay? And I will just choose this. We'll choose this, where omega is the third root of unity. And I wish to somehow, after this transformation, it becomes something that is a match gates signature. Okay? And if I can't do that on both sides, then I would really have collapsed. With me? Okay? So let's look at this. What is going on? I would like to have the inverse matrix. I can do either way. If you do the inverse matrix of this 2x2 and tensor to the 3, you get 8x8. And then you're going to multiply the 0, 1, 1, 1, 1, 1, 1, 1 on the left. So imagine that you have this 1, 1, 1, 1, 1 on this side. And keep this in mind. So you have 0, 1, 1, 1, 1, 1, 1, 1. Okay? So you have this vector sitting there. And I will now compute this particular matrix. It's inverse. I will do the tensor 3. And I get this matrix out. And you just trust me, I computed right. Of course, for the younger people in the audience, they're doing it in real time. Okay. All right, so I have this. Now, I'm going to actually multiply this 0, 1, 1, 1, 1, 1, 1, 1 on this matrix. And I wish to come out with a vector with a dimension that is the signature of some match gates. Okay? Now, of course, this is all somehow out of blue here. I mean, how did you choose this? And how do you know if it's a match gate realizable? And so on. But don't worry about this for the moment, okay? If I succeeded, you can argue. Right? So what is the 0, 1, 1, 1 times this? Well, that's simple. I mean, that's just adding up the last rows, right? Last 7 rows. So even we old folks can do that. So let's do that, right? So you're going to multiply. You see, you're going to add omega minus 3, omega to cancel. Minus 1, minus 1, minus 1, plus 3 cancel. And then that part also cancel. Make sense? So you, in fact, will come out 0. Wonderful. So this is what sort of the holographicness comes out. It's you're multiplying things with these truth values with things that completely abstract, like a Fourier transform type. And you're going to reassemble these values, superimposed on them by these values, and then you get a 0, which then you reinterpret as if it's a Boolean value. Okay? So that's 0, and I hope you just believe me that these are computed correctly as well. Okay? And the upshot is that this, in fact, is the signature of some match gates. You actually can design a match gate whose perfect matching value, when you remove some external nodes, does give you this. Okay?
So I would like to ask a question.
Yes.
At the beginning, all of your tensors live in a space where you have sort of two variables for each edge. Even this 8 tensor, you can interpret it that this is like some free of.
Well, it's a one variable living on two edges. They have to be consistent. That's
and this matrix, this small 2 by 2 matrix, is like changing this basis.
That's right.
Each edge. Oh.
Yes, that's right. It's a basis transformation. That's right. Okay. And that's why I'm changing the tensor contravariantly or covariantly. And this is where perhaps it's a good point to say conjugate versus covariant. You want to maintain this dot product. And so therefore you would like to have the transformation to be inverses of each other so that the value is unchanged when you did this transformation. And so now where comes 7? Well, it turns out that over 7, you can do both sides. And now I have sort of completely omitted mentioning any theory behind this. So far it's just, G, this is great. Why 7? How do you prove it's just 7? Or and what about other things like these? So there are, a substantial amount of work has been done to understand what can be designed, what properties a match gate signature must satisfy, what kind of transformation it can become, and you argue sort of the realizability question, and you have decision questions there. Okay, so this is developed, and it's under that theory that you can't try all of them, right? So obviously you can't. There's some understanding behind this. I'll just encourage those of you who are interested in, please, come talk to me or look at some papers, and there'll be a good deal of material there. But now I'm sort of trying to segue into another part of the talk where I try to give some hint of the dichotomy theorems, which is built on this, some of them anyway. So there are times where you prove things that can or cannot be done, and it frequently eventually comes down to a point where you have a set of algebraic equations and you say, can you solve them? Okay, here's a sort of a pretty random example. Okay, you come up with these quantities and you say, I would like to set it so that there are solutions of x and y and t non-zero, such that these three are the same and non-zero and the last is 0, so forth. Okay. If that happens, then your desired match gates happen, or actually in this case, your hardness proof will go through. Okay, so it's a sort of a requirement expressed in terms of algebraic equations. And it turns out that you actually can prove this for every c other than 1, that this is true. But for c equal to 1, the proof fails. And not only that, it really corresponds to perfect matching and match gate signature, underlying this. And if you could have proved this, then you would have collapsed. So, in some sense, what I'm about to say now is these dichotomy theorems now is to carve up a wide class of these problems that are sum of product computations. And what you like to prove is that in every single case, it is either in polynomial time or sharply complete. And you leave nothing in between. And these proofs sort of tells you that exactly when it fails. And when it fails, it happens to have this very non-trivial algorithm. And this is sort of perhaps a point I will come back at the end of the talk. But it's sort of like, if P were to equal to sharp P, then it would be very hard to imagine that somehow the proof will just elude us by knowing this unsuspecting algorithm, which we happen to have discovered in the 60s or 70s. But how come you didn't, what if something that you didn't know? That make sense? I'll come to that later.
Right-hand side here, rational functions, or the way you've written it, it seems like they're rational functions.
Yeah, these are rationals, the T inverse there. Is that what
Yeah.
It's just a simplifying. There's no big deal.
More than systems of polynomial equations, or you can reduce it to
Yeah, you can have two variables in t and t prime, and you inquire that t times t prime equal to 1 of them. That's true. So now I would like to move to at least describe some of the complexity dichotomy theorems that have been proven in this. It comes at least in three different frameworks: graph homomorphisms, constraint satisfaction counting problems, and Holland problems. So what is graph homomorphism? Here's the definition of the partition function of the graph homomorphism. You're given a matrix, a symmetric complex matrix in the undirected case. Okay, so an arbitrary k by k matrix. And the input to the problem is a graph, an undirected graph, G. You should think of this as n by n size. That's the variable, and k is fixed. Okay. And then you think of all possible sums of assignments to the vertices of G with one of those k values. You think of this k as k different colors, perhaps. Okay? Or spins up and down, left and right. And for a particular assignment of the spins, you look at all the edges and you go over to the matrix and say, what would the edge value be? So if you assign the two vertices as 1, 2, then you go to the matrix and you look at the entry A1, 2. Okay? And you multiply all of them. So this is called the partition function of the graph homomorphism. Now, if this matrix, let's imagine the graph. Think of this example. Let's say you have 0, 1, 1, 1. Let's say. Okay. So then you're saying I'm assigning vertices as either 0 or 1. Okay. And then on every edge, you would like to avoid the case where both sides are not taken. So you like to pick subset of vertices so that every edge has at least one side is picked. Right? And so what is that problem? Yeah, vertex cover, right? So that's a vertex cover. And if you do something like a 3 by 3, then you're assigning 3 different names to the vertices so that every edge looks around and say you should not be the same. 3 coloring. So problem with you in the audience. Okay, so I'm trying to explain that these are very elementary things. Okay, you just think about it, and the perspective is that this is a broad generalization of all such sort of locally specifiable edge constraint type questions. It's a special case of the constraint satisfaction. Oh, I have an example here. So this is the K coloring. All right, so now the dichotomy theorem in this particular case, and it's following a lot of partial work where, for example, the initial work by Dyer and Greenhill talks about 0, 1 matrices and non-negative matrices and reals and so on, is to say that if you give me an arbitrary matrix, symmetric complex valued, then this quantity whose input is G, output is this value, is either computable in polynomial time or is Sharpe-Hard. That's sort of an example of a dichotomy theorem.
Computational model, if the entries.
Yeah, so the computational model is really somewhat of a side issue, but you could be very precise. So you can think about them as algebraic numbers, for example. And since the K is fixed, then there's no question of what I mean by this algebraic number as an output in this field. Okay? And but it's more than that. I mean, I can talk to you sideline. It's only involving multiplication and addition. So as long as you have a model where multiplication and addition is meaningful, then this is okay. Now, the graph homomorphism problem can be viewed as a very special case of constraint satisfaction. You have a binary function. Every edge has this binary function sitting on it. And you have both sides coming in, and you just give the value of this constraint function. Okay? And in general, you have the constraint satisfaction problem where you have an arbitrary finite set of constraint functions, and an instance of the problem is a set of variables that take values between 1 up to k, and then a set of constraints taking out of this set of constraint functions. They apply onto the subset of variables, and then you think of all possible assignments, and you sum over of the product. It's a sum of product partition function again. And there we have another dichotomy theorem. It's the same statement. You give me an arbitrary f. The problem is either going to be in polynomial time or Sharpe hard. But there's quite a bit of a different flavor. This theorem uses the previous proof, which was pretty long. But there is a flavor in which this is different. This dichotomy really tells you what set A will give you the polynomial time Z sub A. Okay, it's an explicit, I don't know, explicit is a very overworked term here. But I think you all agree with me that it would be explicit, okay? In a nutshell, it's sort of like some sort of tensor prod, so this A I'm describing, for which you're going to get polynomial time partition functions, are tensor products of Fourier matrices with some rank 1 modifications on top of it. Being a little vague because it's really it's not a simple sentence description. I'm lying a little bit.
It's decidable anyway.
It's decidable in polynomial time, even using a thesis result by Ge, who was a student of Lenstra. And that takes quite a bit of work to get that to be in polynomial time to be decidable. But it's decidable. That's clear. Now, the difference here is that here we have a strange situation where we prove to you for every finite set that defines the CSP problem, the problem is either in polynomial time or Sharpe hard. What does that mean? That means that the f is fixed, and the instance of n variables and m constraints taking out of this f is applied, and that's an instance, and you ask what's the solution. This computational problem, input set of variables, invocation of these f's, and output the value of the sum of product, is either going to be in polynomial time or Sharpe hard. Okay? But we don't really have a way to tell. It's not a contradiction. Okay? We don't have a way to tell if you give me 17 functions f, what case it belongs.
I mean, this is not decidable.
We don't know if it's not decidable. We just don't know a decision procedure. It, in fact, had a predecessor paper, a very beautiful paper, important paper by Bulatov, where the constraint functions are restricted to be 0, 1 valued. Okay? And his proof uses universal algebra techniques, and it was also the situation where, for quite a number of years, that it is known to have a dichotomy, his proof, but it was not known that his dichotomy criteria is decidable. And this was rectified by a paper by Martin, Dyer, and Richard. So you asked me, for example, what is the best you know in terms of decidable dichotomy? It's the case where, this is a paper with Ping Yan too, that if it's a non-negative valued f, so if all the f's are non-negative valued, then this dichotomy theorem is decidable. But it's when it has negative values or even complex values, the situation becomes, in some sense, really tricky. You have cancellations, okay, and this is in some sense where the holographic transformations is trying to take advantage of. The cancellations is a source for which very efficient algorithms can arise. And so this is where some strange magic can happen. Okay. But nevertheless, we have a dichotomy in this case. I think I'm running out of time. So there's this third framework called the matching Holland, which is sort of edges are variables and vertices are constraint functions. Perfect matching is one such example, obviously. Edge coloring is another. Okay? And we currently, for example, have a dichotomy that includes the edge coloring problem, which has been open for at least several decades. So what's the question? You color edges with kappa different colors. And at the vertex, the constraint is that they are all different. Okay? And you want to count the total number of valid edge colorings. Make sense? It's a sum of products again. And we show that this Holland dichotomy implies this. I think I'll stop here. If you have any questions, I'd be happy to answer.
Questions?
If we go back to this matrix one, where you
Which one?
back forward, your sharp P versus P dichotomy for the matrix.
For the graph homomorphism,
Yeah.
okay.
So, do you know what kind of subset? Let's say I fix the size of the matrix K by K once and for all. Do you know what the nature of the subset that is in P is like? I mean, is this a closed subset? Is
Yeah.
it neither open nor closed? Is it isolated points? Is it are there a curve?
No,
in there?
we can describe this set very explicitly for every K.
So is it positive dimensional?
Is it a right?
Yeah, that was my next question.
Positive dimension. What do you mean by positive dimensional? I mean, it has.
Most matrices like this or like
No. It's definitely positive dimensional, but it's not full dimensional. If that's what your question.
It's not going to be full dimensional.
Yeah.
But is it the zero set of a collection of polynomials? Is the next question. Is it describable?
No. It has a rank 1 modification for immediately you have the diagonals to be arbitrary, for example. You can modify.
But that's a linear space, arbitrary diagonal.
Yeah.
So that's not a problem.
You have some arithmetic conditions too.
I mean, is it? Yeah, that's what I want to know. Is it arithmetic?
You asked for dimension, right?
Well, that was my first question.
Oh, okay. What's your second question?
I believe you answered it. That
Okay.
It's positive dimensional. you
Right,
said.
right. What is
Okay. Do you know the dimension? Is it so? Our whole space is dimension k squared. Is this dimension 1 or k squared minus?
No, it's not k squared. That would be full dimension. No, it's not.
No. I
The
said
whole
k
space
squared
is
minus
K
1.
squared. He's wondering about your.
Is it square root of k or k or k squared minus 1? Is it a hypersurface? Probably not. It's probably very small.
symmetric, so let's start with k squared.
Okay, sorry. K squared over 2.
I can't do this calculation in my head right now, but it has a very explicit description, but it has several stages. I would guess it's around k, on the order of k.
Okay, so square
could be
root of
missing.
the total space.
So what's the nature of the description? Is the question is it an algebraic set? Is it given by arithmetic conditions?
Yeah, that's what.
It's a so you know what the Fourier transform matrix is?
Yeah, sure.
Okay. You take tensor products of these guys, arbitrary, and then it comes in two varieties. One is called a bipartite type, and one is not. You can put in the bipartite case, you can put in the sort of off diagonal blocks and zeros there, or it is not a bipartite case, then you have a further slight restriction on them, and you put on the diagonal directly. And then for either case, you can do some rank 1 modifications on these.
So is this description of some matrices A which have this property, or all or the characterization of those which do?
This is a description of all the A's that will give you polynomial time computable Z sub A, assuming P is not equal to sharp P. Everything else is sharp P hard. One day, somebody proves P equal to sharp P. The theorem still is valid, it's just meaningless.
So in the first part of the talk, you were talking about counting modulo various numbers, and then the dichotomy theorems. I didn't see it. So
Yeah, that's separate. Yeah, I have honestly too many different things I want to say, and they are not. Let me just perhaps say one more thing which I didn't even get to say, which loops back to the first part. I think, so we have some dichotomy theorems, and these are not for the general domain, called the general domain problems. These are kappa bigger than 2 case. The variables take more than just 0, 1s. If the kappa equal to 0, 1, we have a much more explicit descriptions of what the tractable CSPs are, okay? And it's in that set where we have a closer connection perhaps with the stabilizers and orbits that people here are mostly interested in. And there, one of the theses, which is only proved for the Boolean domain symmetric set of functions, is the following: that all of these problems, these CSP type, or let's think about the spin systems for now. It comes in exactly in three types: those which are polynomial time computable, and then those, I'll lump the second and third for now, that are Sharpe hard. So that's the first dichotomy coming up. But then within those that are Sharpe hard, it actually comes in two different kinds: those which are in planar input that are solvable in polynomial time, but in general case will be Sharpe hard, and those which are Sharpe hard even for planar cases. And then the statement says that the middle class, those which are just planar solvable in polynomial time but generally hard, are precisely those which are transformable under holographic transformations to the match gates computation. And I think that is really perhaps the real import of the introduction of the match gates, that it carves out this class of algorithms that are planar in polynomial time, but in general Sharpe hard. And there's this sort of universal algorithm, which is basically the holographic transformation to the Castalian algorithm. For this class of problems, at least. This is sum of products for local computation. Now, this thesis is only proved, as I said, for the Boolean domain symmetric function set and some asymmetric functions, but not totally proved in the more general sense. And there are lots of open problems in the Holland framework and all of this. So I'll be very happy to have more young people working on this. So maybe I'll just mention some papers that you can look up.
Okay, that's time to speak.
The description of the good set, a very elegant description in terms of an nice variety. It'd be very nice in this